when scientists started studying this and they realized that bonds were not rigid, they were looking around for, then how can we explain what bonds are like? And they hit upon the idea that bonds are like, the atoms are two balls and the bond is like a spring connecting the atom. And this became known as the ball and spring model. Now, it's a model. In other words, it's something that we use to sort of represent reality, but it's not exactly reality, okay? So the atoms aren't really balls and they're not connected by springs, okay? But they act like they are. And the thing is then, because they act like that, we can use analogy. Now, what does that mean? Well, what that means is if we were to actually take large physical balls and hook them up with springs and look at what causes them to vibrate, why do they vibrate bigger, what changes their frequency, things like that, we could say, well, these are the things that cause these balls and springs, you know, like these real balls and springs to do that. Maybe we have similar effects in the atoms. Does that make sense? And so there was a guy who actually studied this, super interesting scientist guy named Robert Hooke in England, was a contemporary of Isaac Newton, did a whole bunch of really cool and interesting stuff, including he was one of the first people to look at natural objects using a microscope. And in fact, he published a book in 1664, something like that, called Micrographia, which was basically like the first biology book, where he looked at bugs and stuff and he drew really awesome pictures and everything. Anyway, super interesting guy, kind of a weird guy. At one point, he decided to study balls and springs. Okay? There was actually a reason. He was trying to figure out how to make a clock that would work on a boat because of issues in navigation, and there was like a huge prize available if you could do it, and he thought balls and springs might work. It didn't work out for him, but that's why he studied these things, okay? So he came up with something called Hooke's law. Now, I'm not even going to write Hooke's law. You don't have to know Hooke's law. You don't have to know the formula, okay? You're not doing calculations with it. All I want you to understand is that Hooke basically found that there were two important things when you were looking at balls and a spring, okay? There were two important things that caused the spring to vibrate at a different frequency, okay? That changed the frequency of the vibration, all right? The first thing was the mass of the balls, okay? And basically there's an inverse relationship. As the mass of the ball increases, the frequency decreases. So if you put heavier balls on an atom, the bond is going to vibrate more slowly. Okay? Little light atoms vibrate really fast. Okay? Everybody cool with that? So what I'm doing here is I'm correlating the mass of the balls with the mass of the atoms, right? The mass of the balls that Hooke measured, it's just like the mass of the atoms in our bond. So bonds with heavier atoms vibrate more slowly, in other words, at a lower frequency. The other thing that he found was you could take the spring and you could make it thicker. You could make it more stiff, harder to stretch, okay? And as the spring became harder to stretch, it would vibrate at a higher frequency, okay? So again, the strength of the spring increases, the frequency increases, okay? Now, what we can correlate that with is whether it's a single, double, or triple bond. So a single bond is a very stretchy, weak spring. A double bond is a little stiffer, right? A little harder to stretch. Triple bond is a really strong bond, very hard to stretch, okay? In general, the stronger the bond, the stiffer the spring, if that makes sense, okay? And so there's another effect we're going to talk about in a little bit. If we make that bond weaker, then it vibrates at a lower frequency, right? Weak bond, low frequency, strong bond, higher. So when we make it weaker, it vibrates at a different lower frequency than we would otherwise expect. Okay, everybody cool with that? That's all you need to know about Hooke's law. Okay, finally then, there's one other thing I want to talk to you about, and that is only polar bonds absorb IR. You have to have bond polarity. Remember bond polarity? Where you have two atoms, they have a different electronegativity. So they make a little dipole moment, right? A little positive, a little negative. You have to have that polarity for the bond to be able to absorb IR. Okay? So what that means is that oxygen to oxygen, like in O2 gas, that does not absorb IR because that's not a polar bond. Nitrogen and nitrogen, not a polar bond. Okay? Everybody cool with that? That turns out to be a good thing. If it weren't for that, then our atmosphere would absorb infrared from the sun, and the Earth and all of its gases and everything would have heated up and everything would have boiled away, you know, billions of years ago. Okay? It's the fact that our atmosphere is transparent to IR because we get a lot of IR from the sun. All that heat, when you go out in the sun, you feel heat on you. That's IR from the sun. Okay? If it weren't for the fact that those gases were transparent to IR, the Earth would have already heated up to where it couldn't sustain life. Everything would have burned away. Okay? This is the problem with global warming, global climate change, is that carbon dioxide, carbon to oxygen bond is a polar bond. So carbon dioxide absorbs IR. So when we put it into the atmosphere, it starts absorbing that heat that's normally transparent. It just comes and bounces off the Earth. Instead, it comes in and gets stuck and the Earth heats up. So if we put more carbon dioxide, Earth heats up more. Okay? Really, really simple, basic science of organic chemistry.